steel teeth strike wet clay. A Marion steam shovel lowers its bucket into the earth with a slow mechanical groan. The dipper handle slides forward along iron guides. Steam hisses from valves along the boiler casing. The bucket weighs nearly 5 tons when full. A steel cable tightens. The machine pulls back. The entire upper structure rotates on a circular rail. Gears grind against each other with the heavy rhythm of early 20th century machinery. Then the bucket opens. Half a truckload of earth collapses into a waiting railcar below. This scene repeated itself thousands of times a day during the construction of the Panama Canal. Each Marion steam shovel could move 300 to 500 cubic yards of earth in a shift. In places where men with picks and wheelbarrows would have needed weeks, the machine could clear the ground in hours. For many people, this machine became one of the symbols of the 20th century, a tool powerful enough to reshape geography. In museums of engineering history, photographs often show these machines standing on the edge of enormous cuts in the Panamanian jungle. Workers appear tiny beside them. The bucket hangs in the air like the jaw of some mechanical animal. The narrative attached to these images is familiar. The canal was once considered impossible. A strip of land only 80 kilometers wide, yet filled with swamps, unstable hillsides, and tropical disease. Early French attempts in the 1880s collapsed under landslides, financial scandal, and catastrophic death rates among workers. But the story usually continues with a turning point. In the early 20th century, American engineers arrived with a different strategy: better disease control, a system of locks instead of a sea-level canal, and most importantly, an army of modern machines, steam locomotives, rock crushers, cableways, and hundreds of steam shovels built by companies like Marion Steam Shovel Company of Ohio. These machines were often described as the true heroes of the canal. In engineering textbooks, they represent a decisive moment. The moment when mechanical power finally surpassed human labor in large-scale earth-moving. School history books frequently frame the canal in similar terms: a triumph of engineering, a demonstration that industrial technology could overcome geography itself. Even in documentaries, the visual language is consistent. The steam shovel swings. Earth pours into rail cars. The jungle is pushed back meter by meter. Machines transform landscape into infrastructure. From this perspective, the Marion steam shovel appears almost inevitable. A logical step in technological progress. A machine that helped humanity connect two oceans. But if we slow down the story and examine it more closely, some details begin to feel less straightforward. Because the historical record surrounding these machines contains elements that rarely appear in the popular narrative. Details that are documented, yet strangely absent from the simplified version of the story. If the Marion steam shovel truly represented a decisive leap forward in industrial capability, why do many accounts of the canal mention the machines only briefly, while entire sections of engineering reports focus on problems that the machines created as often as they solved? And why do certain details about how these machines actually operated in Panama appear frequently in technical documents, but almost never in the public story of technological triumph? By the time the American phase of the Panama Canal project reached full speed around 1907, the landscape of the Culebra Cut had begun to resemble something closer to an industrial quarry than a tropical valley. Rows of steam shovels stood along the slopes. Their tall booms rose above the excavation terraces like cranes in a shipyard. Each machine weighed roughly 90 tons. The boiler burned coal constantly, feeding steam to pistons that powered the hoist engine and the swing gear. At full operation, a Marion shovel could dig a 2 to 3 cubic yard bucket into dense clay or fractured rock every 20 seconds. The bucket teeth slammed into the ground. Steam vented through safety valves. The machine rotated slowly, dumping the load into rail cars positioned on temporary tracks. Then the cycle began again, hour after hour, shift after shift. Seen from a distance, the process looked almost perfectly coordinated. Trains arrived. Earth disappeared. The canal deepened. This was the image often captured in official photographs, an industrial choreography. Machines and railways working together with mathematical efficiency. But the closer we look at the records of the canal excavation, the less stable this image becomes. Because the Marion steam shovel did not operate in isolation, it depended on an entire moving system around it. Each shovel required 6 to 8 rail cars waiting nearby to receive material. Once filled, the cars had to be pulled away immediately by locomotives. If trains were delayed, the shovel simply stopped. A machine capable of moving hundreds of cubic yards per hour could suddenly become motionless, waiting for empty cars. Engineering reports from the canal describe this as one of the constant logistical pressures of the project. At times, more than 150 trains per day circulated through the Culebra Cut to keep the shovels supplied with empty cars. The canal excavation had become less a single machine problem and more a problem of continuous industrial circulation. Tracks had to be moved constantly. Entire rail lines were relocated sometimes several times per week as the cut deepened. Workers known as track shifters followed behind the machines. They lifted rails, repositioned them, and hammered them back into place under tropical heat that often reached 35 degrees Celsius in the shade. Without them, the shovel could not move forward. But even when the logistics worked perfectly, another problem kept returning. The ground itself refused to behave as expected. Much of the soil in the Culebra Cut was not solid rock but unstable clay layers mixed with fractured volcanic material. When steam shovels carved away the slopes, the hillsides sometimes collapsed. Entire sections of the excavation slid downward, not slowly, but suddenly. Historical engineering reports describe landslides that moved hundreds of thousands of cubic yards of earth in a single event. Sometimes these slides buried rail lines. Sometimes they buried the work that machines had just completed. In certain cases, the slide material filled the excavation so completely that steam shovels had to dig the same section again and again. There were days when machines that had been removing earth suddenly became machines digging themselves out of it. One landslide in 1907 reportedly moved more than 2 million cubic yards of material. For weeks afterward, several steam shovels worked simply to clear the collapse. The canal did not move forward during that time. It moved sideways. This detail appears repeatedly in the engineering correspondence of the project, but it rarely appears in the simplified story of technological conquest. Because the machines were not simply cutting through the landscape, they were engaged in a kind of mechanical negotiation with geology, and the ground often pushed back. Another detail also appears frequently in technical reports. Steam shovels were powerful, but they were also fragile in certain ways. Their boilers operated under pressures often exceeding 150 pounds per square inch. Their cables endured enormous stress. If a cable snapped while lifting a full bucket, the steel line could whip across the work site with lethal force. Maintenance crews constantly replaced worn cables, gears, and boiler fittings. Breakdowns were common enough that entire repair shops operated near the excavation zones. In some cases, a single shovel could remain out of service for days waiting for parts or repairs. Yet even with these interruptions, the machines kept digging, slowly widening the canal, producing the visual impression of unstoppable progress. But when engineers wrote privately about the excavation, their tone often sounded less triumphant, more cautious, because the machines that symbolized modern engineering power were operating inside a landscape that repeatedly resisted their control. And this creates an interesting tension in the historical record. The popular story describes the canal as the moment when machines finally conquered nature. Yet the documents written by the engineers who worked beside those machines describe something slightly different. A project where progress was real, but constantly interrupted. A system where enormous machines did not simply dominate the environment, they struggled against it, which raises a quiet question that rarely appears in the simplified narrative. If the steam shovel represented the triumph of industrial technology, why do so many engineering reports from the canal describe excavation as a process that had to be repeated over and over again, sometimes in exactly the same place? The Marion steam shovel quickly became one of the most recognizable machines associated with the Panama Canal. In photographs from the construction years, the machine often dominates the frame. Its boom extends over the excavation pit. The dipper bucket hangs open, teeth dark with mud. Below it, rail cars wait to receive the load. Workers appear as small figures standing beside the tracks. The image communicates something very clear. A machine large enough to reshape the earth, But when we move from photographs and popular accounts to the technical documentation of the canal, the scale of the story begins to change. Because the machines that appear so decisive in the visual narrative were only one element inside a much larger and more unstable system. Engineering reports from the canal rarely speak about a single machine achieving dramatic breakthroughs. Instead, they describe a process where excavation depended on a tightly coordinated network of equipment. A steam shovel digging into the hillside could only work if several other systems functioned simultaneously. Railway dispatching, track relocation crews, spoil disposal zones, maintenance workshops, coal supply for the boilers. Without these supporting systems, the shovel's bucket simply stopped moving. The machine itself did not create productivity. The system around it did. This detail rarely appears in simplified histories of industrial machinery. Instead, the steam shovel is often presented as the decisive technological solution that allowed the canal to be completed. But engineers working on the canal wrote about productivity in more complex terms. A Marion steam shovel might theoretically move 300 cubic yards per hour under ideal conditions. Yet the official excavation reports often recorded far lower averages, sometimes 100 to 150 cubic yards per hour. Not because the machine lacked power, but because the environment constantly interfered with the cycle. Rail cars arriving late, tracks shifting under unstable soil, slopes collapsing into the excavation, or the bucket striking layers of rock harder than expected. In several sections of the Culebra Cut, engineers reported that the machine spent significant time simply breaking loose rock that had to be blasted before it could be removed. In these situations, the shovel did not dig continuously. It waited. The bucket hung motionless in the air while dynamite crews prepared charges. Then the blast occurred. Dust filled the excavation. Fragments of rock scattered across the slope. Only then could the shovel return to work. In other words, the shovel's operation depended heavily on processes that the simplified story rarely emphasizes. Explosives, geological surveys, slope stabilization, drainage systems, all of these shaped the pace of excavation as much as the machines themselves. There is another type of simplification that appears frequently in popular histories of industrial machinery. The claim that machines like the steam shovel dramatically reduce the need for human labor. On the surface, this seems reasonable. A single shovel moving hundreds of cubic yards of earth clearly performs work that would require hundreds of men with shovels. But the workforce records from the canal project show something more complicated. Operating one Marion steam shovel required a team, an engineer controlling the machine, a fireman feeding coal into the boiler, ground workers managing cables and signals, rail crews moving loaded cars away from the shovel, track crews relocating rails behind the excavation, maintenance mechanics responsible for boilers, gears, and cables. Altogether, a single working shovel might depend on 20 to 30 workers directly connected to its operation. And that number did not include the railway crews transporting spoil or the workers maintaining the locomotives. In other words, the machine did not eliminate labor. It reorganized it. It concentrated physical effort into a mechanical core surrounded by layers of support work. This restructuring of labor is rarely emphasized in the simplified version of the canal story. Instead, the machine appears as an autonomous agent of progress, a mechanical hero. Yet the records show that its productivity emerged from a dense network of workers whose tasks rarely appear in photographs or museum displays. There is also a tendency in popular accounts to compress the timeline of mechanization. Images of the canal often suggest a sudden transformation, as if the arrival of American engineers and modern machines quickly turned the project into a smoothly operating industrial system. But the excavation records show a much slower process. The canal project began in 1904. Large-scale excavation using steam shovels expanded gradually over several years. Even by 1907, engineers still reported constant experimentation with excavation strategies. Track layouts were redesigned repeatedly. Spoil disposal zones were moved. New blasting techniques were tested to improve shovel productivity. In other words, the system surrounding the steam shovels evolved slowly, through trial and error, through failure as much as success. This detail complicates another element of the simplified narrative, the idea that the canal represents a straightforward demonstration of industrial superiority, a moment when modern machinery solved a problem that earlier efforts could not. But when historians compare the French attempt of the 1880s with the American construction period after 1904, the differences are not only technological. The French also used steam-powered excavation equipment. They also attempted large-scale earth-moving. What changed in the American phase was not simply the machine itself. It was the scale of organization surrounding the machine. Disease control programs that reduced yellow fever and malaria, massive railway logistics systems, centralized engineering administration, and a workforce that eventually exceeded 40,000 laborers at the peak of construction. The steam shovel functioned inside this environment. It did not create it. This does not diminish the importance of the machine. The Marion steam shovel was genuinely powerful for its time. Its steel boom could extend more than 15 meters. Its hoist engine could lift several tons of earth with each movement of the bucket. But the tendency to treat it as the central explanation for the canal's success may tell us more about how technological stories are constructed than about how the excavation actually unfolded. Because machines make for clear symbols, they are visible, photogenic, easy to place at the center of a narrative. Systems are more difficult to show. Networks of logistics, labor, geology, and maintenance do not fit easily into a single image, so the story simplifies. The machine becomes the protagonist. The surrounding complexity fades into the background, and over time the simplified version begins to feel natural, almost inevitable. Yet when we return to the technical documents, the construction reports, and the daily records of the excavation, a different picture appears. One where the Marion steam shovel was not the singular force that carved the canal, but one component in a vast and fragile industrial ecosystem, which raises a question that historians rarely ask directly. If machines like the steam shovel became the symbols of industrial progress, how much of that symbolism reflects the actual mechanics of history? And how much reflects the human preference for stories built around visible objects rather than complex systems? By the time the Panama Canal opened in 1914, photographs of steam shovels had already become part of a powerful visual language. In many images, the machine stands alone at the edge of the excavation. Its long boom stretches over a trench cut into the hills of Panama. The bucket hangs open. Below it, the ground falls away in layers of clay and broken rock. Workers stand beside the tracks for scale. The composition is almost theatrical. The machine dominates the frame. The earth appears passive. It looks like a simple story. Technology confronting nature. Technology winning. This visual pattern appeared frequently in newspapers, engineering journals, and later in history books describing the canal. The steam shovel became a symbol that communicated something larger than its mechanical function. It suggested that industrial power could reshape geography, that machines represented a new stage of civilization. In the early 20th century, this symbolism mattered because the canal was not only an engineering project, it was also a political statement. The United States had taken control of the canal zone in 1904 after supporting Panama's separation from Colombia. From the beginning, the canal carried enormous geopolitical significance. It would shorten shipping routes between the Atlantic and Pacific Oceans by nearly 13,000 kilometers. Naval fleets could move between oceans in days rather than weeks. Commercial shipping would bypass the long journey around South America. But such an ambitious project also required public justification. The canal demanded enormous financial investment. By the time construction ended, the total cost had reached roughly $375 million in early 20th century dollars. That figure made the canal one of the most expensive engineering projects ever attempted at the time. For governments, projects of this scale rarely exist only as practical infrastructure. They also become symbols. Evidence that a nation possesses technical mastery. Evidence that it can command nature through engineering. In this context, machines like the Marion steam shovel were more than tools. They became visual proof of industrial capability. When newspapers published photographs of the excavation, the machines provided the most compelling image. A hillside cut open by steel buckets, rail cars filled with earth, clouds of dust rising behind locomotives. The shovel represented control. It represented order imposed on landscape, even when the excavation experienced delays, landslides, or logistical complications. These difficulties were rarely emphasized in public imagery. They did not translate easily into the language of technological triumph. A photograph of a landslide burying a rail line communicates uncertainty. A photograph of a steam shovel lifting a bucket of earth communicates progress. So the machine became the preferred symbol. Museums and exhibitions reinforced this narrative. Engineering displays in the early 20th century often celebrated large machines as markers of modern civilization. Steam turbines, steel bridges, ocean liners, and the equipment used to construct the Panama Canal. In these displays, the shovel appeared as a hero of engineering. Its mechanical power represented the triumph of modern industry over geographical obstacles. This symbolism also served economic interests. Companies that manufactured heavy machinery benefited from the visibility of these projects. The Marion Steam Shovel Company and similar manufacturers supplied excavation equipment not only to the canal, but also to railways, mines, and construction sites around the world. The canal provided an extraordinary advertisement for the capabilities of industrial machinery. A machine that could help dig one of the most ambitious engineering projects on Earth was a powerful marketing image. But the symbolic value of these machines also extended beyond industry. For industrializing nations in the early 20th century, machines often represented something broader. A cultural marker of progress. Industrial equipment suggested discipline, organization, and technological competence, qualities associated with modern states. In contrast, regions without such machines were often portrayed as underdeveloped. This contrast appeared frequently in the language surrounding the canal. Before construction, the Panamanian landscape was often described in newspapers as wild or untamed. Dense jungle, unstable hillsides, dangerous swamps. After excavation, the same landscape appeared in photographs organized by railways, locks, and industrial machinery. The transformation seemed to illustrate a broader idea that modern technology could convert chaotic nature into rational infrastructure. The steam shovel fit perfectly into this visual narrative. Its structure made the process of transformation visible. The boom extended. The bucket bit into the hillside. The machine rotated. Earth moved. Few other machines could demonstrate industrial power so clearly in a single motion. Yet this clarity also simplified the story. Because the machine did not represent the entire canal project, it represented one moment in a far more complicated system of labor, logistics, and environmental conditions. But symbols rarely aim for complexity. They aim for recognition, and the steam shovel became instantly recognizable. It condensed the canal into a single image, a steel machine carving a passage through the earth. Over time, that image became the dominant way of remembering the project. Not because it captured every aspect of the excavation, but because it captured the aspect that fit most easily into a familiar narrative. Technology advancing, nature yielding, civilization expanding its reach. When people later described the canal as a triumph of engineering, the steam shovel naturally appeared at the center of the story. Its movements were dramatic, its scale impressive, its function easy to understand. But when we return to the engineering records, the labor statistics, and the operational reports from the canal construction, the picture becomes more layered. The machine was undeniably important, yet the reasons it became the symbol of the canal may reveal something about how societies remember technological achievements. Large machines make powerful images, and powerful images shape historical memory, sometimes more strongly than the complicated systems that actually produced the result. Which leads to an interesting possibility. Perhaps the steam shovel did not become the central symbol of the Panama Canal simply because it was the most important machine involved. Perhaps it became the symbol because it was the machine that most clearly illustrated the story that governments, industries, and societies wanted the canal to represent. A story where progress appears visible, mechanical, and unmistakably powerful. If we move away from the symbolic images of the canal and return to the documents produced during its construction, the Marion steam shovel begins to appear in a different kind of record. Not photographs, not museum displays, but operational reports, daily excavation tables, maintenance logs, engineering correspondence. These documents rarely describe the machine as a heroic symbol. Instead, they treat it as a device inside a demanding industrial routine. A typical excavation report from the canal listed numbers with careful precision: how many cubic yards each shovel removed, how many hours it operated, how many hours it stood idle, how many rail cars were filled, how many times the track had to be relocated. For example, records from the Culebra Cut excavation show that steam shovels were capable of moving large volumes of earth, but only under tightly controlled conditions. When the rail cars arrived on time, when blasting had already broken the rock, and when landslides had not buried the excavation face. Under those conditions, a Marion shovel could remove 200 to 300 cubic yards per hour. But the same reports also show how frequently those conditions disappeared. Heavy rain could transform clay slopes into unstable mud. Rail tracks shifted as the ground settled under the weight of locomotives. Spoil trains occasionally blocked access routes, and landslides remained a persistent problem throughout the construction years. One engineering report from 1908 describes a landslide that moved more than 300,000 cubic yards of material into the excavation zone. In practical terms, this meant that weeks of digging were suddenly reversed. Steam shovels that had been carving the canal deeper now had to remove the collapsed hillside. Again, in the same location, another type of document rarely appears in simplified accounts of the canal: the maintenance reports for excavation machinery. Steam shovels were powerful machines, but they operated under conditions that constantly strained their components. Their boilers required steady fuel. Their hoist cables carried enormous loads. Their gears rotated under heavy torque as the upper structure swung to dump each bucket. As a result, breakdowns were not unusual. Boiler fittings leaked. Steel cables frayed and had to be replaced. Bucket teeth wore down after repeated contact with rock. In some cases, shovels remained out of operation for several days, while mechanics repaired damaged components. This required workshops stocked with spare parts, machinists capable of fabricating replacement fittings, and transport systems to deliver those parts to the excavation zones. The canal project maintained several large repair facilities specifically for heavy machinery. Inside these workshops, workers dismantled steam engines, replaced gears, and repaired broken steel frames. These spaces rarely appear in the visual memory of the canal, but they were essential. Without them, the excavation would have slowed dramatically. Another set of documents adds yet another layer to the story. Labor records. Operating a Marion steam shovel required more than the machine itself. The operator controlled the hoist and swing levers. A fireman fed coal into the boiler, sometimes shoveling hundreds of kilograms of coal during a single shift to maintain steam pressure. Signalmen communicated with locomotive crews. Ground workers guided rail cars into position. Track crews repositioned rails as the excavation advanced. Altogether, the functioning of a single shovel often depended on dozens of workers performing coordinated tasks around it. In the official workforce statistics of the canal construction, the number of laborers employed often exceeded 35,000 people during peak years. Only a small fraction of those workers operated the machines directly. Most were involved in support roles: rail transport, maintenance, track relocation, drainage, slope stabilization, blasting. These tasks rarely appear in simplified narratives of technological progress, yet the documents show that they shape the pace of excavation as much as the machines themselves. Another type of record reveals a different aspect of the canal environment: health and safety reports. By the early 20th century, American engineers had implemented aggressive mosquito control programs to reduce malaria and yellow fever. Drainage ditches were dug. Standing water was treated with oil. Screens were installed in living quarters. These measures dramatically reduced disease compared to the earlier French construction attempt. But working conditions inside the excavation remained difficult. Temperatures in the cut often exceeded 35 degrees Celsius, with humidity close to saturation. Steam shovels operated among dust clouds produced by blasting and excavation. Coal smoke from locomotives drifted through the valley. Workers stood close to heavy machinery and moving rail cars. Engineering reports occasionally mention injuries caused by falling rock, cable failures, or collisions between trains and equipment. These details rarely appear in the simplified story of the canal as a smooth triumph of engineering, not because they were hidden, but because they complicate the image of effortless technological progress. And this is perhaps the most interesting feature of the documentary record surrounding the canal. None of these details were secret. The landslides were recorded. The mechanical failures were documented. The labor structure was carefully counted. The environmental difficulties were described in engineering reports and official correspondence. All of this information existed in plain view. Yet when the story of the canal entered textbooks, museums, and popular histories, the narrative gradually condensed. The thousands of workers became a background. The logistical networks faded from view. The environmental instability became a brief obstacle, and the machine remained at the center. The Marion steam shovel, swinging its bucket, cutting through the hillside, a single visible mechanism representing an immense and complicated system, which suggests something subtle about how historical narratives form. The documents never disappeared. What disappeared was the tendency to integrate all of those details into the main story. If we remove the familiar storyline for a moment, the Marion steam shovel begins to look slightly different. The machine itself remains impressive. A steel structure weighing close to 90 tons, a boom extending more than 15 meters over the excavation, a bucket capable of lifting several cubic yards of earth with each movement. The pistons driving the hoist engine operated under steam pressure strong enough to pull tons of soil from the canal walls. None of that changes. The machine was real. Its mechanical capability was genuine. And without heavy excavation equipment, the canal would have been extremely difficult to build at the scale achieved in the early 20th century. But when we step away from the simplified narrative, the machine no longer stands alone. It becomes one element inside a much larger structure. A structure that included thousands of workers moving rails, maintaining locomotives, blasting rock, repairing machinery, and stabilizing slopes that repeatedly collapsed into the excavation. It included medical teams fighting mosquito-borne diseases, railway dispatchers coordinating hundreds of spoil trains, mechanics rebuilding damaged gear assemblies in repair shops far from the excavation face. It included geological conditions that repeatedly forced engineers to rethink excavation strategies. In that context, the Marion steam shovel begins to appear less like a singular instrument of progress and more like a node in a dense industrial network. Powerful but dependent, efficient but limited by the systems around it. The canal was not carved by one machine. It emerged from the interaction between machines, labor systems, logistics, engineering decisions, and environmental constraints. When historians describe the canal simply as a triumph of machinery, they are not necessarily wrong. But the description is incomplete because the mechanical image that dominates our memory of the canal captures only one layer of the project, the visible one. The shovel swinging its bucket is easy to see. The railway dispatch network coordinating dozens of trains is harder to visualize. The slope stabilization calculations performed by engineers appear only in reports. The daily routines of workers maintaining the machines rarely appear in photographs, and so the visible element gradually becomes the symbol. Over time, the symbol begins to stand in for the entire process. The Marion steam shovel becomes the machine that dug the canal, even though the excavation depended on far more than the motion of its bucket. This does not mean the historical narrative was invented or deliberately distorted. Simplification is a common feature of historical storytelling. Large projects often become associated with the most recognizable object involved. The steam locomotive becomes the symbol of the railway. The blast furnace becomes the symbol of industrial steel. The steam shovel becomes the symbol of the Panama Canal. Each object captures something real about the process it represents, but none of them capture the full complexity. When we return to the documents, the complexity reappears. The landslides, the repair workshops, the rail systems, the environmental conditions, the thousands of workers operating around the machines. All of these elements were always part of the canal story. They were never hidden. They simply did not fit as neatly into the image of a machine carving a passage through the earth. And perhaps that is where the most interesting question remains. If for more than a century we accepted a clear and orderly story of the Panama Canal centered on a powerful machine, how many other technological histories might also appear simpler than they actually were? Not because the evidence is missing, but because certain kinds of stories are easier to tell than the systems that truly produce them?